Recording. Today, what we're going to be doing is we're going to be talking a little bit more about taking a definite integral, which, as we kind of explained last time, is a number. Okay, a definite integral represents, if you're looking at a graph, it can represent the area under a curve. If you're thinking about it from the terms of what a function's representing, say like a marginal cost function, okay, it's the total cost between two x values, but it's a number. We're going to be extending that concept today to talk about antidifferentiation, which is related to the same process, but instead of getting a number, you get a function, okay? So you get a total function back from a marginal function. So this whole idea of integration, you want to think about as being kind of the reverse process of differentiation. If I start with a total function and I differentiate it to get a marginal function, I can anti-differentiate back with an additional piece of information to get the original function back again. Okay, likewise, if I have a rate function and I want to know what's the cumulative value of whatever that rate's talking about between two x's, I can use a definite integral to get that. Okay, but the process is going to be the same. And your text holds off on bombarding you with processes and formulas for actually doing this because they want to kind of make it clear what this all represents. Okay, it's really important to get the concepts down first as far as, you know, does this make sense, what's going on here? Okay, rather than just memorizing a bunch of formulas and pushing the symbols around, okay? So that's kind of why it may seem like it's a little slow getting off the ground. And some of you did contact me and say, you know, I really don't understand why I'm trying to use calculus to do this thing with the table to figure out the total value. I can kind of just do that with regular arithmetic. And it's sort of, yes, I know, but, you know, kind of play along so that the concepts make sense to you. Okay, calculus without understanding the concepts is really frustrating because it's hard to apply it to anything. Okay, and we want you to be able to come out of here and actually do useful stuff. Okay, not just do math book problems. Okay, so I'm going to begin the way I usually do with sharing my browser just to show you where we are. Okay, you can see we're still in week 10 of our course. Okay, we did definite integral last time. And now what we're going to be talking about is something called the Fundamental Theorem of Calculus, which is related to the definite integral, and then antidifferentiation. So kind of like a more general use of an integral. Okay, so that's what we're doing today. And again, I'm going to be using fundamental theorem and antidifferentiation notes if you're following along. Okay, and as far as assignments for this week, you can see we've got 2 homework assignments and a discussion board. Okay, again, optional notes. This is not something you have to look at, but these apps that sometimes are down here in supplementary materials can be really helpful. I showed you this one last time, the Desmos app for approximating a definite integral. Okay, so let me get the chat open in case anybody has questions while we're getting ready. But give me a minute while I get these fundamental theorem and antidifferentiation notes open. Okay, let me share that with you. All right, so everybody should see my notes, fundamental theorem and antidifferentiation. And again, I've excerpted these from your text, but again, just be forewarned, it isn't everything that's in your text, so you may still want to, you know, go through that and pick up some of the extra examples that, you know, I didn't get a chance to do with you. Okay, so they start out, you know, kind of, I guess you could say over the top, saying this section contains the most important and most used theorem of calculus? Well, it's called fundamental for a reason, okay? It forms the basis of virtually half of calculus, the integral half of calculus, as opposed to the differentiation half. It's from the 17th century. It was independently developed, okay, or discovered. I think developed is a better word, okay, by Newton and Leibniz, two towering mathematicians in the past, right, at least in Western tradition. And what it does is it relates derivatives and integrals. And it's kind of something that we use a lot, okay, as the foundation. A lot of foundational stuff is kind of hidden, but it does form the basis of a lot of mathematics, okay? So if we look at this, you can see I've got an integral sign here, this elongated sum sign, and it says if you take a rate function, notice the prime here on the function f, okay? If I basically take a rate function and I divide it into these tiny little rectangles that are dx wide, right? And then I take the limit where I let dx go to zero, approach zero, and I have an infinite number of these intervals, right? These rectangles, and I add them up from a to b, right? How can I do that? Well, notice this function doesn't have a prime on it, okay? So this is the total function f, okay? You can take that total function evaluated at b and take the total function evaluated at a and just subtract them to get the value of the definite integral, okay? That's kind of one way to do it, all right? And we haven't shown how to go from f prime of x to f of x, okay? We haven't shown that. In case you're wondering, did I miss something? You didn't, okay? Here it is in words, right? The definite integral of a rate from a to b is the net y units, the change in y that accumulates between a and b, okay? So it's just basically what's happening to y as you move from a to b. Another way to visualize that, it's the area under the curve, okay? The net y units, okay? So basically, we're saying here is if we could figure out a way to get this function f without the prime, that'd be a whole lot easier than approximating with rectangles, okay? So again, it's going backwards through the differentiation process, okay? That's essentially what we're doing. We're undoing differentiation, okay? So let's take a look at some of these examples, okay? It says, if you know that f prime of x is 2x, find f of x, okay? So you have the rate function. Whoops, sorry. Set for something else. Have the rate function, and you want the total function. Whoops. Okay, now you might remember from doing derivatives that the way you got 2x as a derivative was by differentiating x squared. Okay, if I say, let's say f of x is x squared, if I differentiate this to get f prime of x equals 2x, that'll work. Okay, you'd be right. The problem is any number of functions with a constant tacked on will also work, okay? Because remember, when you differentiate a constant, you get 0 in f prime of x. So you lose some information, the information that was contained by that constant, okay? So again, one way to write it, if I write it with differentials, the derivative of x squared is 2x. Okay, the derivative of x squared plus 2 is also 2x, because the 2 constant here doesn't give me anything in the derivative. Likewise, the derivative of x squared minus 5 is 2x. Okay, so you can see when we go forward with differentiation, we lose a piece of information, namely whatever this constant was telling us in the original total function. Okay, so what does this mean? It means you've got infinitely many functions that all have the same derivative. Okay, so again, my function f of x could be x squared. It could be x squared plus 2. It could be x squared minus 5. It could be x squared plus 150. And I have no way to tell unless you give me another piece of information. Okay, and we'll talk about that in a minute. Okay, now the derivative tells you the shape of the function. Okay, we know x squared, right? That's a parabola. The derivative's telling you about the rate of change of this parabola. Okay, think about it from a point of view of college algebra. What does a plus 2 and a minus 5 do to the graph of x squared? Okay, so I'm asking a question. What does plus 2 or minus 5 do to the graph of x squared? What does it do to the graph? Anybody remember from college algebra? Right. Okay. Ni is saying it shifts it up and down, right? So if you take this graph, x squared, it's sitting on the origin with its vertex on the origin. If you add a plus 2 to it, you're just shifting it up 2 units. So now its vertex is at the point 0, 2. Likewise, if you start with this graph and you say minus 5, okay, you're moving it down on the y-axis. So now its vertex is at 0, -5. You're not doing anything to change the shape of the graph, though. So its rate of change everywhere will be the same. Okay? So basically, the derivative tells you about the shape of the function. Okay? So its rate of change isn't affected by the constant. By a shift. Let's put it that way. It's not affected by a shift. Remember, the sliding a graph around without stretching it or compressing it, okay, it's called a shift. Okay, and that's what these constants are doing. They're just shifting up and down. Okay? So basically, this gives us a situation where I'm trying to find an antiderivative function, okay, for f prime of x equals 2x, and I have an infinite number of them to choose from. Well, I don't want to write down lots and lots of functions. I want a general way to show that my antiderivative will be x squared with any number of constants attached to it. And the constant could be 0. That would give me this one. The constant could be 2. That would give me this one. The constant could be -5. It would give me this one. So basically, when you want to find an antiderivative, okay, you're basically going to wind up with a constant of integration like this. Okay, so when you find the antiderivative, and we're just doing this based on memory, right? I didn't give you any formulas or processes. I just said, remember when you took a derivative of x squared, you got 2x. Well, now imagine going backwards, okay, and integrating, right? Okay, and notice there's no a and b here, okay? I'm basically saying, what's the antiderivative of this function? And the answer is x squared plus some constant, okay? It's called the constant of integration, and it can be numerically evaluated if you get another piece of information. Okay, so you're going to leave it as C unless they tell you something else that you can use to figure out what C is. Okay, but here is your first antiderivative, right? It's the integral sign without any bounds on it, no a or b here. Okay, some sort of a rate function times dx, right? And we're saying, if you were to sum this function up, the area under this function, you would get a function that's x squared plus some constant. Okay? Everybody understand all the words? Okay, is this clear so far? Clear so far? Okay. All right, so you can see here an antiderivative is not giving us a number, it's giving us a function. Okay? And what's the relationship? Well, the derivative of this function will be the rate we started with. All right, so let's look at the actual definition that's in your text. Okay? The antiderivative of a function is a function, first of all. Okay? Such that, okay, and again, this business with the capital and lowercase f's drive me crazy, okay? So basically, they're just essentially saying this was a rate that you started with. F prime of x, okay? And when you anti-differentiate it, you get f of x, the total function, back again. Okay? The antiderivative is a whole family of functions, and you write them with a constant of integration. Okay? The antiderivative without bounds is called an indefinite integral. So sometimes people will use that terminology. Definite integral has numbers on the top and the bottom of the sum sign, telling you where you're evaluating it between. It gives you a number, okay? Whereas this gives you a function. Okay, so indefinite integral gives a function. Okay, and if you had this, whoops, this gives a number. Okay, and again, the way we're going to do this is when you have this sort of a situation, you don't want to start building tiny little rectangles. It'll take you forever. What we're going to do is we're going to first find the antiderivative of f of x, and then we're going to use the fundamental theorem to just subtract that antiderivative evaluated at the upper bound minus the lower bound. Okay, so antiderivative figures into definite integrals. Okay. All right, so this is just a little box that is vocabulary. It tells you what everything is called. It tells you what the verb forms are. I'm going to use the verb form integrate usually rather than antidifferentiation because that just takes too long to say. Okay. Most people tend to refer to antidifferentiation as an indefinite integral, and the other, okay, is a definite integral, the one with bounds. Okay, so this is definite integral. Okay, so does that make sense to people? Is everybody okay with the terminology? Okay, now is a good time to ask, okay, because if I start using the terminology and you have questions about it, you're going to get lost. Okay, so please ask if it doesn't make sense. Okay. All right, so the next thing they're going to do is show you some familiar things, right? So if you're asked to find the antiderivative of 2x, okay, you're basically going to take an indefinite integral. Okay, of 2x dx. And we said, okay, what would I have had to differentiate to get 2x? That would be x squared. But as we showed before on the previous page, Any one of a number of constants could have been attached to that, including no constant, a zero, okay? So we have to put the constant of integration there, okay? So you need a C, you always need a C when doing antidifferentiation. That rather than saying that, let me say when finding an indefinite integral. Okay, so C is required. Okay, you always need C. Okay, here's another really familiar function. Everybody remember when you differentiate e to the x, you get e to the x. Okay, so if I integrate e to the x dx, I'm going to get e to the x plus c. Okay. So again, what you want to imagine here is this function on the left is your rate function, your derivative, okay? And this process is giving you back the function it came from, okay? And again, I haven't given you rules for doing this, okay? This is just based on memory. We remember, yeah, 2x is the derivative of x squared, e to the x is the derivative of e to the x. Yeah, okay. All right, there are no rules yet. Okay. Here's another way to think about figuring the fundamental theorem out. Okay. This is just a restatement. It's not anything different. Okay. If you take the definite integral of a rate, okay, that is your antiderivative of your rate function evaluated at the upper bound b minus the antiderivative of the rate function evaluated at the lower bound a. Okay, and what's important in the discussion here is it gives the net change in the original function. Okay, so net change. So another way to do this is to solve this equation for f of b, okay, which is another way of saying the amount you end up with is what you start with plus the net change as you go along. Okay, this is just another way to show you how it works. Okay, so all they did here was to solve this equation for f of b. How they do that, they added f of a over here. Okay, and now it's in front of the integral sign. Okay, so let's take a look at how this works. And again, the point of all this, nobody really does it this way. I mean, there is numerical solving of integrals, but nobody's really doing it this way. They're showing you this to make sure the concept makes sense. So this lets you get values for an antiderivative as long as you have a starting point and you're able to tell something about the area under the rate curve, okay? So they're saying, suppose capital F of t has the derivative little f of t. So this is a rate. And is f prime of t. Okay, it's a rate. And suppose we know that f of 0 is 5. Okay, so this is the total function. At 0. Okay, that's the value of the total function. So now they're going to use this additional way of looking at the fundamental theorem. Okay, and suppose you want to know, find the values. Okay, they want you to find the values for f of 1 and f of 2. Okay, so this is again, they're trying to find the values of the total function given just what we know about the rate function. Well, okay, here's the alternative form of the fundamental theorem. Okay, so they're saying, well, let's let a equal 0 and let b equal 1. Okay, and then let's plug in those numbers and see what we can find, okay? Well, we know f of 0 was given to us as 5, right? That was given piece of information. And then this piece here, we can approximate from the graph or actually calculate, because everything is right angles. Okay, so this is just asking us for the area under the rate curve from 0 to 1. What's that? That's this. Okay, and you can see that's a triangle. It has a base of 1 and a height of 1. Okay, so if you look down here, you can see they plugged in the 5 for f of 0. And here's the area of the triangle. Okay, so here's the given f of 0. And then the triangle's area from 0 to 1. Okay, this turns out to be a half. So basically, you've got f of 1. Okay, the value of the total function at 1 is 5.5. How would you find f of 2? Well, that would be f of 1 plus the definite integral from 1 to 2 of the rate function, right? This is kind of the accumulated value, like they said up here, right? The net change. Okay? Because again, what's this rate function telling us? It's telling us about the net change in our total function. It's a rate. Okay, so that's what it's telling. All right, so starting point. Plus net change. Okay, so net change in f. That's what we're doing. Okay, so I figured out that f of 1, I've done already, that was 5.5. Okay, that's the previous step. All right, and then I need to figure out how much what's the area under this curve from 1 to 2. So that's this bright blue stuff. Okay, that also looks like it's 1/2 because it's a triangle, 1/2 base times height. Okay, its base is 1. Okay, that's from 1 to 2, and its height is 1 high. Okay, and you can see that gives me 5.5 plus another half. Okay, so the value of my total function at x equals or t equals 2 is 6. Okay, so everybody understand, get the idea of using a starting point, a starting value, I guess I should say, then adding the net change. Okay, everybody understand the concept? Okay. Okay, they told us that up here. Okay, so basically up here you can see given information. Suppose we know that. Okay, so it was given to us. Okay, you need a starting point. No worries. Okay, please ask if you have questions. I love questions. I get real nervous when people aren't asking questions. Okay, everybody good with that one? Okay, let's look at another example like this. All right. I want to do two things. They're showing derivatives here, okay, as well as integrals, but let me start with this. Yeah. Okay. We aren't being told what a of 0 is, okay? So what we're looking at here are the derivatives of the integral, okay? And this is a concept we'll get back to in a minute, okay? So if we basically say, what's the value of the derivative of a at 1, okay? But you want to think of the derivative of okay, the derivative of the integral is the function you started with. Okay, so this part is showing you that derivatives and integrals kind of undo each other. Okay, they undo each other. All right, everybody okay with that? All right, so basically, a prime of 1 is just the value here, right? It's f of 1. A prime of 2 is f of 2. And a prime of 3 is f of 3, which is also 2. Okay, so all this is showing you is that if you take a derivative of an integral, you get the function that was the integrand to start with. Okay, they undo each other. Okay, that's all that's showing you. Now let's take a look at this one. Okay, and I know a lot of folks really hate these questions, but they're important as far as your conceptual understanding. Okay, here is a graph that shows g prime of x. Okay, so here's a rate. Sketch the graph of g of x. It's antiderivative. And make sure it satisfies the condition that g of 0 is 0. So they're telling you something. The value at 0. They're telling you some information about the graph. Well, okay. Well, let's get started. Okay, so this is going to be g of x, and that's x. And I know this point needs to be on the graph, right? G of 0 is 0. Okay, now again, remember, the graph on the left is the derivative of the graph on the right. Okay, so the graph on the left is the derivative of the graph on the right. Okay, if I look at this graph, this derivative graph, I notice that the derivative is 0 when x equals 2. Okay, the derivative is 0 when x equals 2. Everybody see that here? All right, so obviously that's going to be significant. So let's put some numbers on here. Okay, we also know the derivative is positive on the interval, let's just say negative infinity to 2. The derivative is negative on the interval 2 to positive infinity. Okay, does everybody see how I'm getting that from the graph? Okay, the derivative is 0, its y value is 0 when x is 2. the derivative, namely the y value, okay? So these all refer to y values. Okay, so the y value of the derivative is 0 when x is 2. The y value of the derivative is positive to the left of x equals 2, right? From negative infinity up to 2. The y value of the derivative is negative to the right of 2. Everybody see that, okay? What do these facts about the derivative tell you about g of x? What do the facts about the derivative tell you about g of x? Can anybody give me one thing that those facts? There's 3 facts there. So just pick one of them and tell me, what does that tell you about the derivative? Anybody have any ideas? How about the first one? The first one's probably the easiest one. What does it mean when the derivative is 0 at some x value? What does it mean when the derivative is 0 at some x value? What does that tell you? Anybody have any ideas at all? We just spent like 8 weeks taking derivatives of things and setting them to 0. What were we trying to find? Okay, I'll put some other helps in the chat. 0 derivative, horizontal tangent line, extreme value. Zero derivative means you have a horizontal tangent line at that point. It also means you have a turnaround point, right? So you have an extreme value, either a maximum or a minimum at that x value. It's a critical number, right? If you start with a function over here, okay, which we don't know yet, we're trying to build it. But if I had this function and I wanted to differentiate it, okay, basically anywhere the derivative 0, okay, like it is here at 2, means I have an extreme value there. Does that make sense to you? Okay, the derivative is 0 at 2. That must mean I have a critical number there. These are polynomials, right? So I know there's nothing weird going on. I'm going to have a local max or a local min there. Okay. How about the other 2 things about the positive derivatives on the intervals? Okay. What does a positive derivative on an interval tell you about what g of x is doing on that interval? Remember, it's a rate of change. Okay, so what's a positive rate of change? Guys, you're getting me really nervous. I know you know this. Okay. Okay, but positive rate of change usually means you're on the right track, Nee. Positive rate of change means the graph is increasing. Okay, don't get it confused with the second derivative. Okay, second derivative positive, right? You're thinking concave up. Okay, so basically, let's think about first derivative, right? If you've got a positive rate of change, it means the g of x is increasing on that interval. Okay, so let me draw a dotted line at 2 because 2 is obviously something important, right? So we're saying the function is going to be increasing on this interval, right? Because my derivative has a positive sign. And because the derivative has a negative sign, it's decreasing on the other side. Okay? Right? So if it's increasing up to an extremum and decreasing away from it, right? So increasing to the left of 2, decreasing to the right of 2. That's what all that information tells me about g of x. Okay? So is the extreme, extreme value a max or a min? So what do you think? Is the extreme value a maximum or a minimum? If I increase toward it and decrease away from it, what do you think? Yeah, it's a max. Okay. Again, you're increasing up to it and decreasing away from it. Also, if you remember, since this is a derivative, it looks linear, right? That must mean your original function was quadratic because when you differentiated it, you dropped the degree by 1. So I would propose that our function looks something like this. Okay, and again, I don't have any information about too many of the y values or where, how high up the max is or any of that. But I can draw a parabola and I know it's upside down because I need to have a maximum. Okay. Does everyone understand this example? This is a very important example. Okay. And if it's not clear to you, please ask questions. Okay. Please ask questions if you don't understand. We did lots of these graphs starting here and creating this graph. Now all you're doing is reversing the process. This is the derivative graph. What does it tell you about the function? Well, it tells you where the critical numbers are, where the graph turns around, right? Has maxes and mins. And it also tells you where the graph is increasing and decreasing. And again, remember, when you're looking at the derivative, you're looking at y values, positive y values, increasing graph, negative y values, decreasing graph, right? Because these are rates of change. Okay, right? Questions on anything so far? Questions on anything so far? Okay. All righty. I'm just giving folks a minute to see if they've got anything. Okay. All right. So let's talk again a little bit more in detail about the derivative of the integral. We had one problem like that without formalizing it, trying to get you to think about what's going on. But here's the formal relationship, right? If your total function, okay, is the definite integral, right, of your rate function. Then if you differentiate that, you get the rate function back. Okay. This is like the example we did on the previous page where we said, if you take the derivative of an accumulation or total function, you get the original rate function back. All right, that's just showing that antidifferentiation or integration and differentiation and undo each other. They're kind of opposite operations. Okay? Okay. Let's take a look at another example. All right, so here we have, okay, a rate function f of t, and we're saying let capital F of t be the derivative, the integral of that, okay, and they want us to estimate f prime of 3, okay? So basically they're saying the function f, capital F, measures the area from t equals 0 to some x value. To estimate f prime of 3, we want to estimate how much the area is increasing when t is 3. And the value of the function f there is 0, it won't be increasing or decreasing. Okay, so f prime of 3 is 0. Okay, and again, you can see that, well, little f of 3 is also 0. Okay, so this means the area isn't increasing or decreasing. When t is 3. Okay, and you can see it right here from the graph. You can see that f of t is 0. Okay, so that's kind of like what we did before. Let's take a look at some more examples. All right, these examples, again, preliminary to them actually launching a whole bunch of rules and processes for you, which will be what we get into next week. They just want you to play around with verifying, okay, that they came up with the right integrals, okay? So they're saying verify that capital F of x is an antiderivative of this integral. Use part 2 of the fundamental theorem to evaluate, okay? So we want to verify is I guess I should say is an antiderivative. Since there are an infinite number of them thanks to that constant, okay? So how would I do that? Well, I could start by differentiating it. Okay, the ddx means take the derivative with respect to x. And what does that give me? That gives me 3x squared plus 0. Or 3x squared. Okay. And then they say use part 2 of the fundamental theorem to evaluate the definite integral. Well, okay, so the integral from 1 to 4 of 3x squared dx is going to be, okay, it's antiderivative evaluated at the lower bound and at the upper bound. Okay, so basically, now that I have the antiderivative, all I need to do is evaluate it at 4. So this is going to be 4 cubed plus 2 upper bound minus 1 cubed plus 2 lower bound. Okay, so in case you can't see where these numbers are coming from, okay, here's 4, there's 4, there's 1, there's 1. Okay, so I'm just plugging in the upper bound into my antiderivative, okay, and then my lower bound into my antiderivative. So here's the antiderivative. Okay, and then the rest of it is just arithmetic. Okay, so 4 cubed, that's 64, plus 2, minus 1 cubed is 1, plus 2 is 3. Make sure you do whatever operations are in the parentheses first before you subtract. Okay, so this is going to be 66 minus 3. So the total value of the integral is 63. Okay, and what is that? That's actually the area under the rate curve from 1 to 4. Okay, this is a stretched parabola, so the area under it will really take off. Okay. One thing I want to show you for those of you who have a TI-84 is your TI-84 will evaluate definite integrals within constraints. Okay, remember we said if your graph goes below the x-axis, the definite integral has a negative sign below the x-axis, so it'll net out, okay, your area. But let me just show you how the TI works. I'm going to bring up my TI and share that with you for those of you who have a TI. All right, so turn it on and clear it. Okay, I can go into my y equals, all right, and I can put in 3x squared, my rate function. Okay, and then I'm going to graph it on a standard axis. So I'm going to go zoom 6. Okay, and you can see that that really shoots up. Okay, so here's 1, 2, 3, 4. By the time I get over here, that's like way up there. Okay, on your calc menu, which is second trace, you'll notice there is a definite, there's an integration one down here, and it looks like an indefinite integral, but it's not. Okay, if I click 7, it's going to ask me for the lower limit of my integration. Okay, well, in this example, it was 1. So I'm going to type in a 1. Then it's going to ask me for the upper limit of my integration. I'm going to type in 4. And it will shade the area that it's trying to calculate. See 63 down here? Okay, so the TI-84 is definite integrals and will net out any negative area. Okay, everybody all right with this if you've got a TI? And again, how'd we get to it? From second trace, it's on your calc menu. Okay. I just want to make sure you see that. Okay, here's the last problem we'll talk about today. Verify that f of x is the antiderivative of the integrand, okay? And use part 2 of the fundamental theorem. Okay, so verify. Okay, and how would I do it? I would differentiate, okay, ln of x. Okay, and I know that will give me 1 over x. Okay, so that is what is the integrand, right? So I know they anti-differentiated it properly because when I differentiate it back, okay, I get the function that I started with, just like they told you in the last yellow box, okay? Then what I want to do is I want to actually evaluate the definite integral. So the definite integral from 1 to 5 over 1 over x dx What is that? It's the antiderivative ln of x evaluated from 1 to 5. Okay, so here's my antiderivative. And now I'm going to evaluate it at the upper bound. I'm just plugging in the upper bound for x minus the lower bound. Okay. All right, and again, you can leave it that way. Okay, you can also approximate it if they want an approximate. This is an exact value. Okay, also you might realize ln of 1. What's ln of 1? Let's bring up the calculator again and clear it. Okay, this is a 0. Okay, why is that? ln of 1 is asking you, what do I have to raise e to get 1? Okay, e is the base of the natural log. Okay, well, anything to the 0 is 1. Okay, so that's why this is 0. So really all you're evaluating is ln 5, if you wanted to approximate it. So approximately 1.609. Okay, so again, please pay attention to whether or not you need an exact value, in which case you leave ln in, you just say ln 5. Okay, and if you have to approximate it, you're going to get a certain amount of error because you're leaving off decimal places. Okay, now we showed you some of these obvious ones like verify, but let me go back to this one. Okay, we know that if we started with x cubed, okay, and we differentiate it, okay, how did we do that? We basically brought down the 3, right? And then we subtracted 1 from there, okay, to get 3x squared. So you can see if I did x4, I do the same thing. Bring down that and then subtract, right? And that would give me 4x cubed. How would you put it back together? How would you go the other way? Well, you've got to reverse the steps. And not only do you have to reverse the steps, but you've got to do them in the reverse order. Okay, so when we differentiate, the first thing we do is bring down the exponent in front, and then we decrement the exponent. Okay, so if we go the other way, the first thing we're going to do is increment, add 1 to the exponent. And instead of multiplying by the exponent, we're going to divide by the new exponent. Okay, so to go the other way, I'm reversing the steps of differentiating. Okay, the steps are bring down the original exponent and multiply it by what's there, then decrement or decrease the exponent by 1. So to reverse the process, first increment the exponent by 1, and then instead of multiplying, divide by the new exponent. That reverses all the steps. So let's actually try it with a value. Okay, let's say I want to integrate 3x squared dx. Okay, let me use my new process. Okay, first thing says add 1 to the exponent. Okay, so that's 2 plus 1. Okay, the next step says divide by the new exponent. Okay, so x 2 plus 1 over 2 plus 1. All right, so here's the add 1 to the exponent. Here's the divide by the new exponent step. So here's step 1, here's step 2. And then let's just simplify what we got. 3 times x to the 2 plus 1 is 3. 2 plus 1 is 3. What do you know? I got x cubed. Okay, so that's how you get it without somebody handing it to you. Okay, this is called the power rule for integration. Okay, and it's just the reverse of the power rule for differentiation. Okay, so we're not only reversing whether we're multiplying or dividing, whether we're adding or subtracting, but we're also doing the steps in the reverse order. Okay, so I'm showing you how I actually used my homemade rule, okay, to get the antiderivative. Okay, so let me ask at this point, questions? Questions on anything? Okay, questions so far? Okay, again, they tried to give you a kind of a conceptual introduction to integrating before they bombard you with a whole bunch of rules. When I took, a long time ago, when I took calculus, it was like a whole bunch of rules, and then you were left to fend for yourself as to what all this meant. Okay, so we're trying to explain what it means before we show you all the rules. Okay, all righty. I'm going to come back to the meeting. Stop sharing. Okay, and one more time, questions on anything? Questions on anything? You're in good shape to do the homework for those first 2 sections on integration. And again, please make sure to ask me if you have questions.